All right, so let's move on to subroutines. Now, this is a step towards more structured programming. So here I'm going to call a subroutine here with a call statement. So I call the hello subroutine using a parameter, WS name. Here I just define a name, which is Dolly, and I call the subroutine, and the subroutine is not in this file. This is the caller file. Here's the subroutine file, a separate file. And that has to have an ID here. The hello sub is, of course, going to have to match exactly the hello sub in the call. And instead of a data division, I have a linkage section in the data division here. So that has an ls name variable. And these data structures in the linkage section have to exactly match in type and size the data structures are being passed in. That's how you pass in arguments. So you pass in the WS name, and it's a 20-letter string, and that has to match right here, this 20-letter string, and you now refer to it down here with this ls name. So that's how you do it, and when you compile it, you'll have to compile both source codes, caller and hello. So that will combine these two source codes into one executable, which will now call it and say, hello, Dolly. So that's the simplest example of a subroutine. And now you can do a more complicated problem like factoring. So here, I'm going to go through I'm going to ask a question. Is J a factor of I? You type in I and J. Then it's going to call the divider subroutine using several parameters, WSI, WSJ, and WS factors. And I and J are 2-digit numbers, and factors is a 1-digit number. And this subroutine is going to return a 1 or a 0. If it's a 1 that comes back, then it's going to say it factors it. If it's a 0, it doesn't factor it. And so here is the divider subroutine that does that. It has a linkage section. Notice you got both a linkage section for the variables that came in from the calling routine, and you have a working storage section for local variables used only in the subroutine that are not passed in or passed back. And notice that there is no distinction made between parameters coming in and parameters going back. So the I and J come in, and the factors is the data that goes back. And the linkage just links them all to the same memory location. So they're all what you would call global variables in a more modern language. And that's the game. So now I just do a division. You can use the divide verb, and that gives you a remainder. And then you can just check the remainder. If the remainder is 0, then of course it's a factors, and that's a 1. Otherwise, it's a 0. So compiling these two together makes a statement where I can put in 10 and 2, and it will say 2 factors 10. But if I put in 10 and 3, then 3 does not factor 10. So now that you can do that, you can find factors, and now you can find prime numbers by just trying all the lesser numbers and see if you can find any extra factors. And if there are no factors, then it's a prime number. And you can find a variety of prime numbers here for some challenges. And then you can do a problem which caught my attention because I saw chat about this where people talked about how to convert numbers into ASCII in COBOL. And they had like hundreds of lines of code to do this. In fact, one guy said his best solution was to have 255 if statements in a row. But I couldn't believe it was that hard. And I found it's not that hard if I settle for a very much simpler problem, which is just to convert letters to ASCII that are printable letters from A to Z. If I'm willing to make it that simple, then I can make a to ASCII subroutine where I pass it a letter and I'm going to get back an ASCII code. And all you have to do here is make a string with all the letters and a numerical string with all the codes and match them up. So that can be done. So make a program that will turn A into 65 and B into 66 and so on for just the capital letters. And looks like I did the underscore also. So anyway, that's the game. Then make the inverse program. And now you can convert codes to ASCII with 2 digits per character and back from it. And then you can do modular arithmetic. You know, modular arithmetic is like a clock. Here's modulus 9. You have numbers from 0 through 8. If you add 1 to 8, you're back to 0. If you add 2 to 8, you're around to 1. So that's modular arithmetic, and this is important for encryption, because when you encrypt, say, bytes, they turn into other bytes. They never roll off the end and turn into larger things. You just go around rings. So you can now create modular arithmetic, where you can add and subtract numbers and even multiply numbers on a modulus. So you can do multiplication on a ring. 2 times 5 is 10, and modulus 9, that's 1. And so if you can do multiplication on a ring, you might want to do division, but there is no division. This is a problem. And this is a big deal in cryptography, like RSA cryptography, which we're going to get to next. So if I have a message that consists of these numbers, and I want to encrypt them with a ring, I could double them, modulus 9. So doubling 3 is 6. Doubling 7 is 14, but that wraps around the ring and turns into 5. Doubling 4 is 8. Doubling 8 is 16, which is 7. So this is the encrypted version of it, where you have doubled those numbers on a ring. And to reverse the doubling operation, there is no division. You can't divide by 2. So what you do is you multiply by 5. 5 is the multiplicative inverse of 2 on a ring of mod 9. And so if you take things that have been doubled and you multiply them by another 5, it wraps around to where they started. So that's called the multiplicative inverse. And finding the multiplicative inverse of something on a ring is actually not a trivial problem. And so you can do that here in very simple ways. You can find a multiplicative inverse. There are faster methods, but one simple thing to do is just try every number until you find one where the original number you multiplied by and the multiplicative inverse turn into 1 on the ring. So anyway, that's another little challenge there, and there's a few multiplicative inverses to find here, like find the multiplicative inverse of 999 mod 1337. So you have to multiply 999 by a lot of integers until you find one that turns it into 1 mod 1337. Anyway, save this one.